Okay, we're going to continue with our lecture, and we're going to next look at pressure exerted specifically not just by any fluid, but by a gas. In the previous part of the lecture, we said that in a liquid, that pressure was caused by the weight of the fluid, but for a gas, it's a little bit different. So here we have a picture showing a container that's got a gas in it, and there's a little gauge here showing the pressure. The atoms and molecules of gas are basically flying around in the container, and when they strike the walls, they hit the walls and they rebound. And we know that the walls of the container must apply an impulse to the molecules to make them change direction. They're moving with a direction, they hit the container exerts a force on the molecule over some period of time that creates an impulse which changes the momentum, and so the molecule will bounce off the container. So the container is exerting a force on the gas when the gas molecules rebound off of that surface. Now, by Newton's third law, we know that the gas molecules must also be exerting a force on the container. Now, if you take all of these collisions on average, you'll find that there's a force exerted across the container surface. And if we divide that force by the area, that will be the pressure exerted by the gas on the walls of the container holding the gas. Now, what happens if the gas is more dense? There's more molecules and atoms of gas per unit volume. It's more dense. Well, that means there's going to be more collisions per unit time, and because there's more molecules colliding with the walls of the container, there's more molecules in the container. So that means that you're going to have more collisions per unit time, and that means a greater force and a greater pressure. So in the last slide, we saw that the number of gas molecules and atoms in the container matters, but also the volume of the container matters. So if I have this container here, and you can see there's a piston, if I compress this piston to reduce the volume, I've got more molecules of gas per unit volume striking the container, and that's going to increase the pressure. But there is a relationship between the pressure and the volume. Under the conditions where the temperature of the gas is held constant, it's not allowed to heat up or cool down, then the relationship is that the pressure of the gas times the volume of the gas is constant for all different volumes and pressures. And so if I pick any two, so I've got this situation has a particular volume and a particular pressure, I compress the piston so that the temperature doesn't change. This guy now has a new volume and a new pressure, but if I multiply them together, the pressure of one times the volume of one, that would be this guy, will equal the pressure of two times the volume of two. So let's do our check our understanding checkpoint here. And question number 1 says, a piston in an airtight pump is withdrawn so that the volume of the air chamber is tripled. What's the change in pressure? Now, in the previous slide, we saw Boyle's law, which tells us that the pressure times the volume is equal to a constant. And so question 1 is saying the volume goes up by 3 times. So this guy goes up times 3. And so what must the pressure do in order to keep constant? It has to go down times 3. And so the volume goes up by a factor of 3. The pressure has to go down by a volume of 3. So the pressure will be cut in third. Now the second question says, a scuba diver breathes compressed air from beneath the surface of the water. If she holds her breath while returning to the surface, what happens to the volume of her lungs? The answer is nothing good. So what's going to happen? The pressure decreases as she rises to the surface. Now, if she's holding her breath so that the air in her lungs can't escape, the pressure on the outside of her body is being reduced, And so the volume in her lungs, the volume of the gas in her lungs is going to expand. This is why scuba divers are taught to never hold their breath while they're going up, while they're ascending. Doing so could literally kill you. Now, the next thing that we want to talk about is what we call atmospheric pressure. And if you go out into a park on a sunny day, you are surrounded by air, the entire atmosphere of the earth. And that atmosphere is exerting a pressure on you. And we know, like all fluids, that pressure is caused by the weight of the fluid above it. So imagine a bamboo pole that extends all the way to the very top of the atmosphere. The mass of air that bamboo pole would displace to the top of the atmosphere is about a kilogram's worth of air. And we know that m times little g is about 10. That means that the weight of air above that kilogram would be about 10 newtons. And that's what causes atmospheric pressure. Now, here we can see in figure 5.24, there is a table, and we've selected this blue area, and we're looking at the weight of the air above that blue area. And it turns out the weight of the air that presses down on a 1 meter squared surface at sea level is about 100,000 newtons. And so the atmospheric pressure is about 100,000, and that's 10 to the fifth power, newtons of force for every meter squared of surface. And there's another unit, we say that that's about 100 kilopascal, or 100,000 Pascal. Okay, the next slide, we're going to look at something called a barometer. Barometers are tools that are used to measure atmospheric pressure. This is how we know what the atmospheric pressure is. The way you make a barometer, and of course there are more complicated barometers than this. This is just one kind of barometer that it gives you the basic idea of how you can measure atmospheric pressure. And so you take a glass tube that's longer than 76 centimeters and you fill it with mercury, and then you tip it upside down and you submerge the open end of the tube into a dish of mercury or a bowl or some kind of container of mercury. And so what's going to happen is some of the mercury is going to fall down into the bowl, but there's an atmospheric pressure that's pushing down on the mercury outside the tube, and that's going to create a balancing force. So the weight of this column of the mercury in the tube is trying to be pulled down by gravity, but the atmospheric pressure is pushing up here, and that pushes it back up, and so there'll be a balance level. Now, what happens when the atmospheric pressure out here gets higher? There's more pressure down, and so that's going to push the mercury up the tube. And if there's less atmospheric pressure, then the weight of the mercury will overcome the pressure and the level in the tube will lower. And so by simply watching the level of mercury in the tube, you can tell when the atmospheric pressure is changing. And of course, that's an important thing to know, because atmospheric changes generally occur when the weather is going to be changing. And so this is useful for helping us predict, when it's going to rain or when it's going to stop raining, etc. When, unfavorable weather conditions are coming or when more favorable weather conditions are coming. A barometer is a tool that we can use to help predict the weather.